The proof of this fact is not very complicated, this theorem, but instead of presenting the proof directly, anyway the proof is given in so many books including our textbook, what we shall try to do is to provide the main geometric interpretation or the intuition behind the proof. The main argument of the proof happens to be very close to a well-known result, namely this result. Suppose I have a straight line like this, and I have a point outside the straight line, and I want to find out the least distance from the point to the straight line. And you know that the answer is, if you drop a perpendicular from the point onto the line, then that will give you the least possible distance. If you take any other line like this, any other arrow where the tip lies on the line and the tail lies at that point, the length must be greater than or equal to this. And not only that, this arrow, this minimum length arrow, also happens to be unique. Now, how do you really prove this fact? The proof goes like this, that you just consider this as something like the defending champion, and you take any other line which you consider as the challenger. So you have the challenger and the defending champion. You want to show that the challenger, which also satisfies the condition that its tail is at the point and tip is on the line, must have length greater than or equal to the defending champion. And the way is to use Pythagoras theorem. You just consider this, which basically means you break up the challenger into two parts, the champion plus whatever you get when you subtract the champion from the challenger. So the challenger is champion plus this red vector. And then you notice that this is 90 degree. So if you just apply Pythagoras theorem, you see that squared length of this is squared length of that plus squared length of this. You really do not need to compute squared length of any of these things. You just observe that squared length must be greater than or equal to 0. So squared length of this fellow must be greater than or equal to squared length of this. And that immediately shows this must be having the least possible squared length. How do you show uniqueness? The same idea. Suppose there is some challenger which attains the same squared length as this champion. What does that mean? The same argument shows that this thing must have squared length 0. That is, this vector, this red vector, must shrink to a single point, which immediately says that this tip must match with that tip. So the challenger must be same as that existing champion. Precisely the same idea is applicable to the proof of the Gauss-Markov theorem.